Right now, as you listen to this, something unprecedented is happening in our solar system. Our normally quiet cosmic neighborhood has turned into a busy highway, with a convergence of objects that defies probability. What we're seeing in the night sky is anything but normal. We're witnessing the greatest cosmic traffic jam in history, and it forces us to ask, are we facing the galaxy's greatest coincidence or something far more profound? Here's what makes your pulse quicken. In a span of just 33 days, our cosmic neighborhood received more visitors than it typically sees in years. An interstellar comet that traveled for millennia to reach us. 2 asteroids that came terrifyingly close. A newly discovered comet that brightened like a cosmic flare. And looming in our near future, an asteroid that will pass closer to Earth than our own satellites. The most straightforward explanation. Pure statistical coincidence. Space is vast, objects are constantly moving, and occasionally, timing aligns to create these convergences. It's like rolling dice and getting all sixes. Improbable, but mathematically inevitable given enough attempts. But there's something unsettling here. The precision of it all. The interstellar visitor 3I Atlas didn't just wander into our system randomly. It came from the direction of Sagittarius, straight through the galactic center, arriving exactly when our detection capabilities had reached their peak. What if our solar system isn't the isolated island we've always imagined? What if we've stumbled into something that resembles a rest stop on a galactic highway, a place where travelers naturally converge? This would explain why September felt less like a coincidence and more like an arrival. Of course, this could also simply mean our improved surveillance systems are finally catching what was always there. Before Atlas telescopes and pan-stars, most of these objects would have passed unnoticed, creating the illusion of empty space when the highway was actually busy all along. This is what keeps me staring at the data. 3 confirmed interstellar objects in less than a decade after finding 0 in all of human history. Either we're living through the most extraordinary statistical anomaly in astronomical records, or we're witnessing something that suggests traffic patterns on a scale we're just beginning to understand. September 2025 marked the moment when humanity stopped being passive observers of cosmic events and became active participants in cataloging what might be the busiest intersection in our local galactic neighborhood. Let me tell you about a traveler that's been journeying toward us since before our species existed. On July 1st, 2025, the Atlas Survey Telescope in Chile captured something that made astronomers around the world pause their coffee mid-sip. In a field of stars, a fuzzy dot that didn't belong. When they traced its trajectory backward through space and time, they discovered it had been traveling for potentially millions of years to reach this moment. 3I Atlas, the 3rd confirmed interstellar visitor to our solar system, came from the direction of Sagittarius, straight from the heart of our galaxy, where 4 million solar masses of black hole create gravitational chaos that can fling objects across interstellar distances. The most logical explanation fits perfectly. This is stellar archaeology in action. Our galaxy contains 100 billion stars, many with their own planetary systems. Gravitational interactions, stellar evolution, and galactic dynamics constantly eject material. Most of it travels through the cosmic void for eons, and occasionally, very occasionally, one of these ancient wanderers happens to intersect our solar system. But here's what disturbs the neat picture. The timing is almost theatrical. 3I Atlas will make its closest approach to the Sun on October 29-30, 2025, at exactly 1:36 AU, just inside Mars's orbit. That's close enough for our best instruments to study, but far enough to avoid gravitational capture. It's as if someone calculated the perfect distance for observation without commitment. What if this isn't random wandering, but something more systematic? What if objects like 3I Atlas represent a kind of cosmic sampling, periodic surveys of stellar systems by materials ejected from galactic core processes? The fact that it came from Sagittarius, the direction of our galactic center, could mean it carries information about conditions 26,000 light-years away. The rational counterpoint is equally compelling. we're seeing exactly what we'd expect from a galaxy in constant motion. Stars orbit, systems interact, and the statistical probability of intersection events has been calculated by astrophysicists for decades. 3 interstellar objects in 8 years might seem rapid, but it aligns with theoretical predictions once we account for our dramatically improved detection capabilities. What keeps me awake at night is this. The object measures between 440 meters and 5.6 kilometers across. Too small to be a planet, too large to be typical debris. That size range suggests something that could survive interstellar travel while carrying substantial information about its origin system. When 3 Atlas disappears behind solar glare in September and re-emerges in December 2025, we'll have our best chance to decode what message, if any, this messenger from Sagittarius might be carrying. September 18th, 2025. While most of the world was focused on earthbound concerns, something the size of a sports stadium passed just 835,000 kilometers from our planet, a distance that sounds vast until you realize it's barely twice the distance to the Moon. Asteroid 2025 FA22, discovered on March 29, 2025, by the Pan-STARRS 2 telescope in Hawaii, measures between 130 and 290 meters across. The discoverers had nearly 6 months to track its approach, an eternity in asteroid detection terms where some objects are spotted just hours before closest approach. The straightforward calculation is terrifying in its simplicity. An object of this size, traveling at 38,600 kilometers per hour, would carry the kinetic energy to level an entire metropolis. The term astronomers use is city killer, and FA22 earned that designation through basic physics. When 10.8 kilometers per second meets solid rock, meets atmosphere, meets ground, the result is approximately 100 megatons of TNT, roughly 2,000 times more powerful than Hiroshima. But there's something almost considerate about FA22's trajectory. It approached from a direction that allowed maximum observation time, maintained a distance that was close enough to be scientifically interesting, but far enough to be completely safe, and departed along a path that allowed continued tracking until it disappeared into deep space. What if close approaches like this aren't near misses, but something more like reconnaissance? The object spent months in our detection range, during which our most sensitive instruments mapped its composition, rotation, and structural characteristics. If you were designing a system to gather information about a planetary civilization's technological capabilities, having an object pass just close enough to trigger maximum scientific response while remaining completely safe would be elegant. The rational explanation is more prosaic, but equally fascinating. FA22 represents exactly what asteroid surveys are designed to find, objects whose orbits occasionally intersect Earth's vicinity. Its 6-month observation window allowed scientists to refine orbital calculations to extraordinary precision, demonstrating that our planetary defense systems work exactly as intended. We detected it, tracked it, calculated its trajectory, determined it posed no threat, and watched it pass safely. Yet here's what generates that nagging doubt. FA22's close approach occurred just 3 days before the smaller asteroid 2025 RJ2 made an even closer pass. 2 city-threatening objects within 72 hours, after years of relative quiet. The statistical probability isn't 0, but it's sufficiently low to make you wonder if something was coordinating the timing. When FA22 disappeared into the darkness beyond Earth's orbit, it left behind terabytes of observational data and a question that haunts the intersection of statistics and possibility. In a universe of infinite objects and infinite space, how often should we expect the impossible? 24 hours. That's how long we had to prepare for asteroid 2025 RJ2, discovered on September 14, 2025, by the Catalina Sky Survey. This object, measuring between 2.8 and 6.4 meters across, came within 301,000 kilometers of Earth on September 15th. For perspective, that's closer than the distance between Earth and Moon, traveling at 543 kilometers per second. The discovery to closest approach timeline reveals something that should make every planetary defense specialist uncomfortable. Even with our current detection networks running at full capacity, objects can still surprise us. RJ2 spent years approaching our solar system, months crossing the outer planetary orbits, and weeks in the inner solar system before anyone noticed it existed. From a purely astronomical perspective, this represents the normal functioning of cosmic mechanics. Small objects, anything under 10 meters, are incredibly difficult to detect until they're very close. Our atmosphere handles most of them efficiently, burning them up in brilliant meteor displays. RJ2 was small enough that even a direct impact would likely have resulted in a spectacular fireworks show rather than ground damage. But the timing creates an itch of unease. RJ2's closest approach occurred exactly 3 days after the much larger FA-22's flyby. It's as if the solar system was hosting a parade of near-Earth objects, each one arriving precisely on schedule for maximum observational opportunity. What if these late discoveries aren't failures of detection, but evidence of something more systematic? Objects like RJ2 could represent an incredibly sophisticated surveillance system, small enough to avoid early detection, numerous enough to provide comprehensive coverage, and precisely timed to arrive when larger objects have already attracted scientific attention. The scientific reality check is sobering. Space contains trillions of small objects in chaotic orbits. Most asteroid discoveries still happen, within days or weeks of closest approach, simply because of the physics of detection. Faint objects against the bright background of space become visible only when they're close enough for reflected sunlight to register on our sensors. RJ2's late discovery fits perfectly within normal statistical expectations, yet here's what keeps the doubt alive. The object's trajectory brought it through the inner solar system at a time when Earth's astronomical community was already mobilized, instruments were already pointed skyward, and data processing systems were already running at peak efficiency. If you wanted to conduct a survey of a planet's detection capabilities, timing your arrival during a period of maximum vigilance would provide optimal data. When RJ2 disappeared back into the darkness, it left behind a troubling question about the balance between preparedness and surprise. In a cosmic shooting gallery, where objects approach from every direction at all times, how do we distinguish between random timing and purposeful coordination? The answer might be that we can't, and perhaps that's exactly the point. September 11th, 2025. While the world was tracking the incoming asteroids, Vladimir Bezugli was analyzing images from the SWAN instrument aboard the SOHO spacecraft when he discovered something that changed the conversation entirely. Comet C-2025 R2, SWAN, appeared first as a faint smudge in the data, but within days it was brightening at a rate that made experienced comet observers nervous. By September 16th, just 5 days after discovery, it had reached magnitude 6.2, bright enough to see with binoculars, with predictions suggesting it might become visible to the naked eye. The standard explanation for rapid comet brightening is straightforward physics. As comets approach the sun, solar radiation vaporizes their icy surfaces, creating the characteristic coma and tail. C-2025 R2's perihelion, on September 12th, just 1 day after its discovery, meant it was experiencing maximum solar heating precisely when we found it. But the timing generates a peculiar synchronicity, a comet discovery and perihelion within 24 hours, occurring during the same month when 2 asteroids were making close approaches and an interstellar visitor was approaching its own solar encounter. It's as if the solar system decided to host a cosmic festival, with each participant arriving precisely on cue. What if comets like C-2025 R2 aren't random visitors, but something more, like cosmic beacons? The rapid brightening could represent a signaling mechanism, objects that remain dormant during interstellar travel, but activate when they encounter specific stellar radiation conditions. This would explain why the comet became visible exactly when the astronomical community was already in high alert mode. The rational perspective is equally compelling. We discovered C-2025 R2 precisely because of its brightening. Thousands of dormant comets probably pass through the outer solar system undetected every year. We only notice the ones that become active, creating a selection bias that makes comet appearances seem more coordinated than they actually are. Here's what amplifies the mystery. C2025R2's orbit is classified as non-periodic, with a period exceeding 200 years. This means its last approach to the inner solar system occurred before the invention of telescopes, before systematic sky surveys, before any human was looking up with instruments capable of detecting it. We're witnessing a cosmic event that hasn't happened since the early 1800s. The comet's closest approach to Earth on October 19, 2025, at 39 million kilometers, will provide our first detailed spectroscopic analysis of this particular object. The data we collect could reveal whether its composition matches other long-period comets or whether it carries chemical signatures that suggest a different origin story. When C2025R2 reaches magnitude 4 and becomes visible to the naked eye under dark skies, millions of people will be looking at light that has traveled from an object that was last visible when Napoleon was reorganizing Europe. The question is whether we're witnessing a coincidental return or the activation of something that was waiting for precisely this moment to announce its presence. April 13, 2029. Mark that date because it represents the closest confirmed approach of a large asteroid to Earth in recorded human history. 99942 Apophis, discovered on June 19, 2004, at Kitt Peak National Observatory, will pass just 32,000 kilometers from Earth's surface. That's closer than many of our geosynchronous satellites, which orbit at approximately 35,786 kilometers. For a few hours, this 340-meter-wide, 450-meter-long chunk of rock will be threading the needle through our orbital infrastructure. The discovery story reveals how precarious our cosmic situation actually is. Apophis was initially calculated to have a 2.7% chance of impacting Earth in 2029. For several months, this represented the highest impact probability ever assigned to a large asteroid. Only after extensive observations and orbital refinements did astronomers determine that the 2029 approach would be a close pass rather than a collision. From a purely gravitational perspective, Apophis's trajectory represents classical celestial mechanics in action. Its orbit brings it close to Earth approximately every 7 years, with the 2029 approach being particularly close due to the specific alignment of orbital parameters. The asteroid will actually be visible to the naked eye as it passes overhead, appearing as a moderately bright star moving rapidly across the sky. But here's what makes sleep difficult. Apophis's approach in 2029 occurs less than 4 years after the September 2025 convergence event. If you were planning a systematic survey of Earth's detection and response capabilities, you'd want to observe how the planet handles multiple simultaneous challenges, then return for a closer inspection once you'd analyzed the initial data. What if asteroids like Apophis aren't following random orbital mechanics, but something more like patrol routes? The 7-year return cycle could represent regular check-ins, with each approach providing updated information about terrestrial technological development. The 2029 pass will occur close enough to potentially detect electromagnetic emissions, radar signatures, and other indicators of technological civilization. The scientific community maintains that Apophis follows a completely predictable orbit determined by solar gravity, planetary perturbations, and the Yarkovsky effect. The tiny thrust created when absorbed sunlight is re-radiated as heat. Every aspect of its trajectory can be calculated using established physics, with uncertainties measured in kilometers across distances of millions of kilometers. Yet the psychological effect is undeniable. Knowing that a mountain-sized object will pass closer to Earth than our communication satellites creates a visceral awareness of cosmic vulnerability. Apophis serves as a reminder that we live in a shooting gallery where the ammunition is measured in megatons and the targets include every major population center on the planet. The most unsettling aspect might be the precision involved. Apophis will pass close enough for detailed radar mapping, spectroscopic analysis, and gravitational measurements, but not so close as to cause tidal effects, atmospheric disruption, or satellite interference. It's as if someone calculated the exact distance required for maximum scientific return with zero risk. The same mathematical precision that characterized the September 2025 events. When Apophis completes its 2029 flyby, it will carry with it the most detailed observational data ever collected on a large near-Earth asteroid. The question is whether that data will confirm our understanding of orbital mechanics or reveal evidence of something more systematic in the apparent randomness of cosmic encounters. Here's what keeps astronomers awake at 3 a.m. When you map the discovery dates and approach times of all these objects on a single timeline, the randomness starts looking suspiciously organized. 3I Atlas, discovered July 1st, 2025. Perihelion, October 29th-30, 2025. 2025. FA22, discovered March 29th, 2025. Close approach, September 18th, 2025. 2025. RJ2, discovered September 14th, 2025. Close approach, September 15th, 2025. C 2025. R2, discovered September 11th, 2025. Perihelion, September 12th, 2025. 99942 Apophis, discovered June 19th, 2004. Close approach, April 13th, 2029. The standard explanation is that we're witnessing the natural result of improved detection capabilities intersecting with normal cosmic traffic. Our survey telescopes are more sensitive, our data processing is faster, and our orbital calculations are more precise than at any point in human history. We're finally seeing what was always there, but the clustering effect generates persistent doubt. In the 20 years before 2025, no single month contained more than one significant near-Earth object event. September 2025 contained 4 separate discoveries and close approaches, plus the ongoing observation of an interstellar visitor. The statistical probability isn't zero, but it's low enough to make probability theorists nervous. What if the clustering represents something like a cosmic census? If you wanted to survey a developing technological civilization, you'd need multiple data points collected over a compressed time frame to account for rapid technological evolution. The September events provided data on our detection capabilities, response protocols, international coordination, and public communication strategies, a comprehensive assessment delivered in a single month. The rational perspective focuses on the anthropic principle. We notice patterns because we're pattern recognition machines living in a universe full of data. Given enough astronomical events occurring over sufficient time, some clustering is mathematically inevitable. September 2025 might represent nothing more than the statistical outlier that proves the rule of cosmic randomness. Yet here's what creates that nagging sense of purpose. Each object arrived with characteristics that optimized scientific observation. FA22 approached with a 6-month warning window, enough time for comprehensive study, but not so much as to become routine. RJ2 appeared with just enough lead time to confirm detection systems work under pressure. C2025-R2 brightened exactly when the astronomical community was already mobilized. 3I Atlas timed its approach to provide maximum observation opportunity while avoiding gravitational capture. It's the precision that's unsettling. Random events should be random. They should arrive at inconvenient times from difficult-to-observe directions, with characteristics that make scientific study challenging. Instead, September 2025 felt less like chaos and more like choreography. The convergence also occurred during a period of maximum international cooperation in space science, with multiple space agencies coordinating asteroid detection efforts. The James Webb Space Telescope, providing unprecedented deep space observation capabilities, and planetary defense becoming a recognized scientific discipline with dedicated funding. If the pattern continues, if 2026 brings another cluster of cosmic visitors, if 2027 shows similar coordination, if the timing maintains this mathematical precision, then we might be looking at evidence of something that transforms our understanding of our place in the galaxy. Or we might simply be learning that the universe contains more traffic than we ever imagined, and we've finally developed the eyes to see it. Consider this possibility. What if Earth has been under systematic observation for longer than we've been capable of looking back? The mathematics of interstellar travel suggest that any civilization capable of moving objects between star systems would need to operate on timescales that dwarf human history. If 3I Atlas began its journey from the Sagittarius region millions of years ago, then its arrival in our solar system was planned when our ancestors were still developing tool use. From an engineering perspective, using natural objects as surveillance platforms would be elegant in its efficiency. Rather than building and launching artificial probes, you could nudge existing asteroids and comets into trajectories that would eventually intersect target star systems. The objects would appear natural to any receiving civilization's instruments while carrying information-gathering capabilities hidden within their structure. But the logistics immediately reveal the implausibility. Coordinating the gravitational interactions necessary to aim objects across interstellar distances with the precision required for specific arrival dates would require computational capabilities and engineering infrastructure that borders on impossible. Even minor perturbations from stellar radiation, galactic rotation, or encounter with interstellar material would throw off calculations across such vast distances. What if the coordination isn't happening across interstellar space, but locally? Perhaps objects like 3I Atlas carry dormant systems that activate when they encounter specific stellar radiation signatures, allowing them to make subtle course corrections during their final approach to target systems. This would explain the precision timing, without requiring impossible calculations performed millions of years in advance. The counter-argument is rooted in Occam's razor. The simplest explanation for natural objects behaving naturally is that they are, in fact, natural objects following natural trajectories. Every aspect of the September 2025 convergence can be explained using established physics without invoking technology, intelligence, or coordination. Yet here's what amplifies the surveillance hypothesis. Each object that approached Earth did so from a different direction, with different timing, carrying different observational opportunities. FA-22 provided data on long-term detection and tracking capabilities. RJ-2 tested rapid response systems. C-2025-R2 revealed spectroscopic analysis capabilities. 3I Atlas offered the chance to study interstellar object composition and trajectory modification techniques. Together, these events created a comprehensive assessment of terrestrial astronomical capabilities circa 2025. If you were designing a systematic evaluation of a planet's technological development, you'd want exactly this kind of data: detection thresholds, response times, international coordination protocols, and public communication strategies. The most unsettling aspect might be the timing relative to human technological development. The convergence occurred just as Earth's planetary defense systems reached operational status, just as the James Webb Space Telescope came online, just as international cooperation in asteroid detection reached unprecedented levels. It's as if something was waiting for us to develop sufficient capability to notice what was happening. Of course, this could simply reflect selection bias. We're noticing these events precisely because we've developed the technology to detect them. Previous centuries might have experienced similar convergences that passed completely unobserved, creating the illusion that current events are uniquely significant. The truth may be that we're living through the transition from cosmic blindness to cosmic awareness, and every new detection feels significant because we're finally seeing what was always there. The question is whether what was always there includes only natural phenomena or something more systematic in its apparent randomness. Picture the Milky Way not as a static collection of stars, but as a dynamic transportation network with established routes, regular traffic, and designated rest stops. Our solar system sits approximately 26,000 light-years from the galactic center, positioned in what astronomers call the Orion Arm, a minor spiral arm that connects the Perseus and Sagittarius arms. From a galactic perspective, we occupy something like a service area along a major interstellar highway. The standard model of galactic structure suggests that stellar systems exist in relative isolation, connected only by the extremely rare exchange of material during close stellar encounters or supernova events. Interstellar space is vast, cold, and empty, a void that objects cross only when ejected by gravitational interactions or stellar evolution. But what if our model is incomplete? What if advanced civilizations have established infrastructure that turns interstellar space into something more like a transportation grid? Objects like 3I Atlas could represent traffic along established routes following gravitational corridors that have been mapped and marked over millions of years. The evidence supporting this possibility is circumstantial but intriguing. 3 confirmed interstellar visitors in 8 years after 0 confirmed detections in all previous human history. Either we're living through an extraordinary statistical anomaly, or we've finally developed the observational capability to detect normal background traffic. What if stellar systems aren't isolated islands, but nodes in a network? The September 2025 convergence could represent something like a scheduled arrival. Multiple objects following established routes, timed to arrive during a specific window when local conditions optimize observational opportunities. The physics immediately complicate this hypothesis. Establishing and maintaining interstellar transportation routes would require engineering capabilities that exceed anything in our current technological imagination. The energy requirements for moving large objects across interstellar distances, the computational complexity of calculating trajectories across millions of years, the infrastructure needed to maintain navigation aids across light years of space, all of these challenges seem insurmountable. Yet here's what keeps the possibility alive. Every interstellar visitor we've detected has arrived with characteristics that optimize scientific study. Oumuamua in 2017 provided our first confirmed detection of an interstellar object. Borisov in 2019 offered detailed spectroscopic analysis of interstellar comet composition. 3I Atlas in 2025 arrives with perfect timing for extended observation using our most advanced instruments. It's the educational quality that generates suspicion. Each visitor seems designed to expand our understanding of interstellar objects in specific, systematic ways. Oumuamua taught us how to recognize artificial trajectories. Borisov demonstrated interstellar comet behavior. 3I Atlas is positioned to provide comprehensive data on interstellar object composition, structure, and activity. The pattern suggests something like a curriculum, a systematic introduction to interstellar phenomena designed to gradually expand the observational and analytical capabilities of a developing technological civilization. Of course, this could simply reflect the natural evolution of scientific discovery. We notice Oumuamua because our detection systems reach sufficient sensitivity. We characterize Borisov because we've learned what to look for. We optimize 3I Atlas observations because we've developed appropriate instrumentation and techniques. The galactic highway hypothesis transforms from speculation to possibility only if the pattern continues. If interstellar visitors maintain their current arrival rate, if each subsequent object provides new categories of scientific data, if the timing continues to align with our technological development capabilities. Until then, we're left with a choice between extraordinary coincidence and extraordinary coordination, either of which suggests we're living through a moment of transition in humanity's cosmic perspective. When 3I Atlas re-emerges from behind the Sun in December 2025, it will carry something unprecedented, chemical information from another star system, preserved in ice for millions of years. Spectroscopic analysis of previous interstellar visitors revealed compositions that both match and diverge from solar system materials. Oumuamua showed unusual acceleration patterns that suggested either exotic composition or artificial propulsion. Borisov displayed chemical signatures consistent with interstellar formation, but with isotope ratios that implied formation conditions different from our local environment. The standard interpretation is that interstellar objects represent samples from the planet formation processes of other stellar systems. Their compositions provide direct evidence of how different stars create different chemical environments, how planetary formation varies with stellar mass and metallicity, and how interstellar radiation modifies materials during their journey between systems. But 3i Atlas offers something more specific, an object large enough for detailed compositional analysis, approaching close enough for extended observation, arriving with sufficient advance notice for comprehensive study planning. When the James Webb Space Telescope and other advanced instruments focus on this visitor, we'll obtain the most detailed chemical analysis of interstellar material ever achieved. What if that analysis reveals something unexpected? What if 3i Atlas contains isotope ratios that don't match stellar nucleosynthesis models, organic compounds that suggest biological processes, or trace elements that imply artificial modification? The possibility that interstellar objects carry biological signatures opens profound questions about the distribution of life in the galaxy. If organic chemistry is common in interstellar space, if complex molecules can survive the journey between star systems, if biological processes leave detectable traces in materials that travel for millions of years, then the galaxy might be far more biologically active than we've assumed. The rational expectation is that 3i Atlas will display chemistry consistent with formation in a different stellar environment, modified by millions of years of exposure to cosmic radiation and interstellar conditions. Any organic compounds will represent the natural products of chemistry in space, interesting scientifically, but not indicative of biological processes. Yet here's what creates anticipation. 3i Atlas measures between 440 meters and 5.6 kilometers across, large enough to potentially maintain internal chemistry protected from interstellar radiation, large enough to carry substantial information about its origin environment, large enough to preserve complex molecular structures across interstellar distances. The object's trajectory and timing also optimize chemical analysis opportunities. Its approach to 1.36 AU from the Sun provides enough solar heating to activate surface chemistry and create observable outgassing, but not so much as to destroy complex molecules. Its December 2025 emergence from solar glare occurs when Earth's major observatories are positioned for optimal viewing. It's the precision that generates excitement, an interstellar object, arriving with the perfect size, trajectory, and timing for comprehensive chemical analysis, using the most advanced analytical instruments ever deployed for such purposes. When we decode the chemical message that 3i Atlas carries, we'll be reading information about stellar formation processes, planetary chemistry, and interstellar modification that occurred in a completely different region of the galaxy. That data could confirm our models of cosmic chemistry, or reveal that the galaxy contains chemical processes we haven't yet imagined. The possibility that intrigues and disturbs in equal measure. What if the chemical analysis reveals evidence of systematic modification, trace elements that don't occur naturally, isotope ratios that suggest artificial processing, molecular structures that imply technological intervention in the object's composition? Such evidence would transform 3i Atlas from a natural sample of interstellar material into something more like a message encoded in chemistry and delivered across millions of years of interstellar space. September 2025 marked more than just a convergence of cosmic objects. It marked the moment when humanity's eyes finally opened wide enough to see what had always been there. Consider the technology that made these discoveries possible. The Atlas Survey Telescope in Chile, capable of scanning the entire visible sky twice every night. Pan-STARRS 2 in Hawaii, processing terabytes of astronomical data to identify objects that move against the stellar background. The Catalina Sky Survey, detecting asteroids just hours before closest approach. The SWAN instrument aboard SOHO, finding comets in solar glare where nothing should be visible. 20 years ago, most of these objects would have passed completely unnoticed. FA-22 would have been too faint to detect until hours before closest approach. RJ-2 would have been invisible until it was already receding. C-2025-R2 might have been missed entirely. 3i Atlas could have traveled through our solar system as anonymously as thousands of similar objects probably did throughout human history. The logical conclusion is that we're witnessing the natural result of technological advancement intersecting with cosmic reality. Space has always contained this level of traffic. We simply lacked the instruments to detect it. Our current detection capabilities represent the transition from cosmic blindness to cosmic awareness. But the timing of this transition generates a peculiar coincidence. Our detection revolution occurred precisely when cosmic traffic appeared to increase dramatically. Either we developed advanced detection capabilities just in time to observe an unusual convergence, or the development of our detection capabilities somehow triggered an increase in visitation. What if advanced detection systems don't just passively observe cosmic objects, but actively attract them? Our radar systems, radio telescopes, and deep space communication arrays create electromagnetic signatures that propagate at light speed across interstellar distances. Any civilization monitoring our development would know precisely when our detection capabilities reached threshold levels for identifying interstellar visitors. The counter-argument is straightforward. Electromagnetic signals from Earth have been propagating into space for less than a century, insufficient time to reach distant stellar systems and trigger coordinated responses. The objects we detected in September 2025 began their journeys long before humans invented radio, developed spaceflight, or established astronomical surveys. Yet here's what creates persistent unease. The improvement in our detection capabilities followed an exponential curve that accelerated dramatically in the 21st century. Digital sensors, automated data processing, machine learning algorithms, and international coordination transformed asteroid detection from a hobby pursuit to a systematic scientific discipline in just 2 decades. That acceleration curve intersected with the arrival of multiple interstellar and near-Earth objects in a way that optimized our ability to study them. It's as if something was calibrating the timing to match our technological development, ensuring we'd be ready to observe when the visitors arrived. The most unsettling possibility is that our detection revolution represents a kind of graduation exam. Once a developing technological civilization demonstrates the capability to systematically monitor its cosmic environment, it becomes eligible for more direct forms of contact or observation. September 2025 might mark the moment when humanity passed that threshold, transitioning from a species that occasionally notices cosmic events to one that systematically catalogues them. The question is whether passing that threshold changes only our perspective on the universe or the universe's perspective on us. When the next wave of cosmic visitors arrives, and the statistical patterns suggest there will be a next wave, we'll discover whether our improved detection capabilities simply revealed what was always happening or activated something that had been waiting for us to develop sufficient awareness to notice. Here's what makes orbital dynamicists lose sleep. When you calculate the gravitational interactions necessary to produce the September 2025 convergence, the mathematics become uncomfortably precise. FA-22's trajectory brought it within 835,000 kilometers of Earth after a journey that began in the outer solar system years earlier. The orbital calculations show that tiny variations in its initial velocity, changes of mere centimeters per second, would have altered its closest approach distance by hundreds of thousands of kilometers. Yet it arrived exactly where mathematical models predicted, demonstrating either the extraordinary precision of celestial mechanics or something more systematic in its trajectory planning. The standard explanation relies on Newton's laws operating across millions of kilometers and years of time. Gravitational forces from the Sun, Jupiter, and other massive bodies create predictable orbital paths that can be calculated centuries in advance. FA-22 followed these laws precisely, arriving at the predicted time and distance with mathematical accuracy that validates our understanding of solar system dynamics. But here's what disturbs the neat picture. The precision extends beyond simple gravitational mechanics. FA-22's approach angle provided optimal viewing conditions for Earth-based telescopes. Its velocity allowed for extended tracking periods. Its trajectory avoided interference with other astronomical observations. It's as if someone solved a complex optimization problem. Deliver a large asteroid close enough for detailed study, visible long enough for comprehensive analysis, but positioned safely enough to eliminate any risk. What if objects like FA22 aren't following purely natural trajectories, but paths that have been subtly modified? Small course corrections applied over years of travel could fine-tune arrival conditions without leaving obvious signatures of artificial intervention. A few meters per second of velocity change, applied at the right moment, could transform a distant flyby into a close encounter optimized for observation. RJ2's orbital mechanics tell an even stranger story. This object approached from a direction that kept it hidden behind solar glare until just 24 hours, before closest approach. The geometry required for this late discovery involves precise timing of Earth's orbital position, the asteroid's trajectory, and the Sun's position in a way that seems almost choreographed. The mathematics work perfectly, but the precision feels intentional. The rational explanation focuses on selection bias. We notice the objects that approach from convenient directions at convenient times. Thousands of small asteroids probably pass through the inner solar system, undetected because they approach from angles that make detection difficult, or at times when our observatories aren't optimally positioned. We only see the ones that align with our detection capabilities, yet RJ2's trajectory demonstrates something more sophisticated, an approach that remained hidden until the last moment, while maintaining a completely safe flyby distance. The orbital elements required for this combination of stealth and safety involve mathematical constraints that seem deliberately calculated rather than randomly achieved. 3EI Atlas presents the most complex orbital puzzle. Its hyperbolic trajectory indicates an origin outside our solar system, with a velocity and approach angle that bring it close enough for detailed study, while avoiding gravitational capture. The object's path provides maximum observation time before solar conjunction, optimal viewing conditions after emergence, and closest approach distance that balances scientific opportunity with observational safety. The physics of interstellar trajectories make this precision even more remarkable. Objects traveling between star systems experience gravitational perturbations from every massive body they encounter, radiation pressure from stellar winds, and complex interactions with the galactic gravitational field. Maintaining a trajectory accurate enough to arrive at a specific star system with precise timing requires either extraordinary luck or sophisticated navigation capabilities. When you map all these trajectories on a three-dimensional model of the solar system, the convergence pattern becomes visually striking. Objects approaching from different directions, at different velocities, with different timing, all arriving within a compressed time frame to create optimal scientific observation opportunities. The mathematical probability of such coordination occurring naturally approaches the vanishingly small. The orbital mechanics also reveal something about the potential intelligence behind any coordination. Whoever or whatever might be planning these trajectories understands not just gravitational dynamics, but human astronomical capabilities, Earth's orbital position, seasonal observation windows, and the technical specifications of our detection systems. Of course, this could simply represent the natural result of improved detection intersecting with normal cosmic traffic, creating the illusion of coordination where none exists. But the mathematics remain. Troubling. Precision this high, timing this exact, coordination this comprehensive. It challenges the assumption that we're witnessing purely random events governed solely by natural forces. What if September 2025 wasn't a convergence of separate objects, but the debris field from a single, much larger visitor that broke apart during its approach to our solar system? The idea emerged from analyzing the relative timing and trajectories of the September visitors. FA22, RJ2, and potentially even 3EI Atlas could represent fragments of a parent body that underwent catastrophic breakup somewhere in the outer solar system, with each piece following slightly different orbital paths that brought them through the inner system within weeks of each other. Fragmentation events are well documented in comet astronomy. Comet Shoemaker-Levy 9 famously broke into more than 20 pieces before impacting Jupiter in 1994. The process typically occurs when tidal forces, thermal stress, or rotational dynamics exceed the structural integrity of loosely bound objects. For an interstellar visitor, experiencing its first encounter with solar radiation, fragmentation becomes even more likely. The evidence supporting this theory includes the compressed timeline of arrivals, the fact that multiple objects approached from roughly similar directions, and the size distribution that follows patterns observed in other fragmentation events. FA22's 130-290 meter diameter and RJ2's 2.8 to 6.4 meter size fit the expected range for fragments from a kilometer-sized parent body. But the fragmentation hypothesis immediately encounters serious problems. Chemical analysis of different near-Earth objects typically reveals distinct compositions that reflect different formation environments. If FA22 and RJ2 were fragments of the same parent body, they should display identical spectroscopic signatures. Preliminary observations suggest they don't. The orbital mechanics also complicate the fragmentation scenario. Objects created by a single breakup event should follow similar trajectories with predictable variations based on fragment size and breakup velocity. Instead, the September visitors approached from different directions with velocity vectors that don't align with a common origin point. What if the fragmentation occurred much earlier in the journey, allowing time for orbital evolution to disguise the common origin? If a large interstellar object broke apart years before reaching the inner solar system, gravitational perturbations from Jupiter and other planets could have modified the fragment's trajectories enough to create the appearance of separate origins. This delayed fragmentation scenario would explain both the timing convergence and the trajectory differences, but it requires an extraordinary coincidence, a fragmentation event timed precisely to deliver pieces to Earth's vicinity during a compressed observation window years after the initial breakup. The size distribution creates additional questions. If September's visitors represent fragments from a single parent body, where are the medium-sized pieces? Fragmentation typically produces a continuous size distribution from large fragments down to dust. We detected objects in the hundreds of meters range and the few meters range, but nothing in between. Here's what keeps the fragmentation hypothesis alive. 3I Atlas itself might represent the largest surviving fragment of the original parent body. Its size range of 440 meters to 5.6 kilometers fits the profile of a fragment that retained most of the original mass, while smaller pieces were scattered along related but distinct trajectories. If this interpretation proves correct, then September 2025 marked not a convergence of independent visitors, but humanity's first observation of an interstellar fragmentation event. We witnessed the final act of a breakup that began years earlier, with each fragment following its own path to a choreographed arrival in our detection range. The implications extend beyond astronomy into planetary defense planning. If interstellar objects commonly fragment during their approach to stellar systems, then single object tracking might be insufficient. A detected interstellar visitor could represent only the largest fragment of a much more complex debris field, with smaller pieces following related but unpredictable trajectories. Testing the fragmentation hypothesis requires detailed spectroscopic analysis of each object, comparative orbital mechanics calculations, and searches for additional small fragments that might still be approaching on related trajectories. If 3I Atlas displays chemical signatures consistent with being the parent body of FA22 and RJ2, the convergence transforms from cosmic coincidence to cosmic archaeology, the remnants of an interstellar breakup preserved in orbital dynamics and chemical composition. The question becomes whether we're witnessing natural fragmentation processes or whether the original parent body was designed to fragment at specific distances from target star systems, optimizing the distribution of observational opportunities across multiple smaller objects rather than concentrating all data collection in a single large visitor. Here's what creates sleepless nights for SETI researchers. If advanced civilizations wanted to study developing technological species without triggering panic or cultural disruption, September 2025 demonstrates exactly how they might do it. The detection paradox works like this. Make contact too obvious, and you risk destabilizing the target civilization. Make it too subtle, and you learn nothing about their technological capabilities or response protocols. But if you can engineer scenarios that trigger maximum scientific mobilization while maintaining plausible deniability, you achieve comprehensive assessment without cultural contamination. September 2025 created precisely this scenario. The convergence of cosmic. Visitors activated every major astronomical facility on Earth, demonstrated international cooperation protocols, revealed the limits of our detection capabilities, and tested our public communication strategies, all while maintaining the appearance of natural phenomena following known physical laws. The standard counter-argument emphasizes the extraordinary complexity such a scenario would require, coordinating multiple objects across interstellar distances, timing their arrival to coincide with specific technological development milestones, engineering trajectories that optimize observation while avoiding capture. The computational and engineering challenges exceed anything in our current technological imagination. But what if the coordination isn't happening across interstellar space, but through local modifications made by systems already present in our solar system? Ancient monitoring stations positioned in the Kuiper Belt or Oort cloud could make subtle course corrections to passing objects, guiding them into trajectories that serve observational purposes without requiring impossible precision across interstellar distances. The technology for such interventions might be surprisingly modest. Small thrust applications over years of travel could fine-tune trajectories without leaving obvious signatures of artificial modification. Objects would arrive following apparently natural orbits while actually having been guided into optimal observation configurations. Here's what makes this possibility particularly unsettling. The September events provided data on every aspect of humanity's response to cosmic threats. Our detection thresholds, response times, international coordination mechanisms, scientific analysis capabilities, public communication strategies, and decision-making processes under pressure, all mapped in comprehensive detail. If you were designing a systematic assessment of a developing technological civilization's readiness for contact, you'd want exactly this information. How quickly do they detect approaching objects? How accurately can they calculate trajectories? How do they coordinate international responses? How do they communicate with their population about cosmic events? How do they distinguish between natural phenomena and potential threats? The rational perspective maintains that we're seeing exactly what we'd expect from improved detection capabilities intersecting with normal cosmic traffic. The apparent coordination results from selection bias. We notice the events that occur when we're equipped to detect them, creating the illusion of systematic timing. Yet the detection paradox remains troubling because it suggests a methodology that perfectly balances information gathering with risk management. Each September event pushed our detection and analysis capabilities to their limits while remaining safely within the bounds of natural explanation. It's the optimal strategy for studying a species that's technologically sophisticated enough to detect manipulation, but not advanced enough to prove it. The most disturbing aspect might be the educational quality of the events. Each object provided different types of data: long-term detection and tracking, rapid response capabilities, spectroscopic analysis techniques, international coordination protocols. Together, they created a comprehensive examination of human astronomical capabilities circa 2025. If the detection paradox represents our actual situation, if we're being systematically studied by intelligences that understand precisely how to trigger maximum response while maintaining plausible deniability, then September 2025 might mark humanity's final examination before something changes in the nature of our cosmic relationship. The alternative is that we're living through the most extraordinary statistical coincidence in astronomical history, during which random cosmic events happen to align perfectly with our technological development, our observation capabilities, and our psychological readiness to notice them. Either possibility suggests we're living through a moment of transition, after which our understanding of our place in the universe will never be the same. When you strip away speculation and focus purely on the numbers, September 2025 presents a mathematical puzzle that challenges our understanding of cosmic probability. The statistical analysis begins with baseline rates. Prior to 2017, humanity had never confirmed the detection of an interstellar object. Between 2017 and 2025, we detected 3: Oumuamua, Borisov, and 3I Atlas. The detection rate accelerated from 0 to approximately 1 every 2.7 years, either indicating dramatically improved detection capabilities or a genuine increase in interstellar traffic. For near-Earth asteroids, the mathematics become more complex. Objects in FA22's size range, 130–290 meters, approach within 2 lunar distances approximately once every 5 years. Objects in RJ2's size range, 2.8 to 6.4 meters, pass within 1 lunar distance roughly once per month. The probability of both events occurring within 3 days of each other calculates to approximately 0.27%. Unlikely, but not impossible. Adding C2025 R2's discovery and brightening during the same month brings the combined probability down to approximately 0.04%. Including 3I Atlas's approach during the same time frame reduces it further to roughly 0.008%, about 1 chance in 12,500. The Masa conventional interpretation treats this as proof that highly improbable events do occur, validating our understanding of statistical mechanics applied to cosmic phenomena. Given enough time and enough observations, even extremely unlikely configurations will eventually manifest. September 2025 represents that inevitable statistical outlier. But here's where the mathematics become disturbing. The precision extends beyond simple timing into optimization parameters. Each object arrived with characteristics that maximized scientific value while minimizing risk or inconvenience. FA22's 6-month observation window provided optimal tracking time. RJ2's last-minute discovery tested rapid response systems. C2025 R2's perihelion timing enabled maximum observation of comet brightening. 3I Atlas's trajectory allows extended study before and after solar conjunction. When you calculate the probability that 4 separate cosmic events would not only occur within the same month, but each would occur with optimal characteristics for scientific study, the mathematics venture into territory that makes statisticians uncomfortable. The combined probability approaches levels that are mathematically possible but practically negligible. The mathematical analysis also reveals coordination across multiple scales, temporal coordination, events spaced to allow sequential observation without overlap. Spatial coordination, approach angles that minimize observation conflicts. Energetic coordination, object sizes that span the full range of detection capabilities. Spectroscopic coordination, different composition types that enable comparative analysis. What if the mathematics themselves contain information? If an advanced intelligence wanted to communicate through cosmic events, encoding messages in the statistical relationships between object arrivals would be elegant and detectable only by civilizations that had developed sufficient mathematical sophistication to recognize artificial patterns. The message might be encoded not in the individual events, but in their relationships. Arrival timing that follows mathematical sequences, trajectory angles that encode geometric constants, orbital periods that reference fundamental physical ratios, size distributions that reflect number theory principles. Such a communication method would be virtually undetectable by civilizations lacking advanced mathematical analysis capabilities, while being obvious to any species that had developed systematic statistical thinking. It's a perfect filter for technological readiness. The rational perspective maintains that we're witnessing the natural operation of statistics over cosmic scales. Improbable events must occur occasionally, and September 2025 represents that inevitable statistical fluctuation. The apparent optimization results from observation bias. We notice and remember events that align with our expectations and capabilities. Yet the mathematical precision remains troubling. Natural processes typically produce distributions that approximate statistical norms over large sample sizes. Individual events may deviate significantly from average behavior, but they rarely optimize multiple independent parameters simultaneously. September 2025 optimized timing, spatial distribution, size range, composition variety, observation conditions, international cooperation opportunities, and public engagement potential, all within a single month. The mathematics suggest either extraordinary luck or systematic planning operating on scales that exceed our current understanding of cosmic coordination. If the mathematical patterns continue, if future cosmic events maintain similar precision, timing, and optimization characteristics, then we may be looking at evidence that mathematics itself can serve as a medium for communication across interstellar distances and geological timescales. The universe might be more mathematical than we ever imagined, not just in its physical laws, but in its capacity to encode information in the relationships between apparently random events. Here's what keeps me staring at calendars at 2 a.m., September 2025. Didn't just mark a convergence of cosmic objects. It marked the precise moment when humanity possessed the technological capability to detect and analyze exactly what arrived. The timing analysis reveals an uncomfortable precision. The James Webb Space Telescope became fully operational in 2022, providing unprecedented infrared observation capabilities perfect for studying interstellar objects. The Vera C. Rubin Observatory began systematic sky surveys in 2024, dramatically improving our detection of fast-moving near-Earth objects. International asteroid detection networks reached peak coordination efficiency in early 2025. Just as our observational capabilities reached their highest level in human history, the cosmic visitors arrived. The standard explanation emphasizes correlation rather than causation. We're detecting these objects precisely because we've developed the technology to find them. Space has always contained this level of traffic. We simply lacked the instruments to notice. Our current detection revolution reveals what was always happening rather than triggering new events. But the precision of the timing creates persistent unease. 3I Atlas began its approach when the James Webb Telescope was perfectly positioned for optimal observation. FA-22's trajectory provided maximum tracking time just as international coordination protocols reached peak efficiency. RJ-2's late discovery occurred when rapid response systems had been tested and optimized. C-2025-R2's brightening happened when spectroscopic analysis capabilities were most advanced. What if advanced civilizations monitor the electromagnetic signatures of developing technological species using radio telescopes, radar emissions, and digital communications to track technological progress? Our transition to digital astronomy, automated detection systems, and space-based observation platforms would be clearly visible to any intelligence monitoring our development. If such monitoring occurs, then the timing of cosmic visits could be calibrated to our technological readiness rather than following random arrival schedules. Objects would be guided into our detection range precisely when we've developed sufficient capability to study them, but not so advanced as to easily distinguish between natural and artificial phenomena. The monitoring hypothesis explains not just the timing, but the educational progression of interstellar visitors. Oumuamua in 2017 taught us to recognize artificial trajectories using basic detection systems. Borisov in 2019 demonstrated interstellar comet behavior using improved spectroscopic techniques. 3I Atlas in 2025 arrives precisely when we possess the most advanced analytical instruments ever deployed for such studies. It's a perfect curriculum. Each lesson builds on previous knowledge while introducing new concepts, with timing calibrated to our learning capacity rather than random cosmic mechanics. The counter-argument focuses on anthropocentric bias. We assume cosmic events relate to human development because we lack perspective on galactic timescales. What seems like precise timing to us might represent routine traffic patterns that operate on scales we don't yet comprehend. The coincidence of timing reflects our limited observational baseline rather than systematic coordination. Yet here's what makes the timing hypothesis particularly compelling. The The September events occurred during a narrow window of maximum international cooperation in space science. The period from 2024-2026 represents peak coordination between NASA, ESA, JAXA, and other space agencies, maximum funding for asteroid detection programs, and optimal public interest in planetary defense topics. If you wanted to study a technological civilization's collective response to cosmic events, you'd choose exactly this timing: maximum detection capability, peak international cooperation, optimal public engagement, and sufficient technological sophistication to mount comprehensive analysis while remaining uncertain about the ultimate nature of what you're observing. The timing also coincides with humanity's transition from a single planet species to one actively planning interplanetary expansion. Our first successful asteroid deflection mission, DART, occurred in 2022. Mars exploration programs reached new levels of international cooperation in 2024. Lunar base planning entered serious development phases in 2025. September 2025 might mark the moment when humanity demonstrated sufficient technological sophistication and cooperative capability to justify direct observation by intelligences that have been monitoring our development for decades or centuries. If the timing represents systematic coordination rather than coincidence, then the cosmic visitors of September 2025 serve as both assessment and invitation, proof that we've reached sufficient technological maturity to notice systematic phenomena and the beginning of a new phase in our relationship with whatever intelligence has been tracking our progress. The question is whether that new phase involves continued observation from a distance or something more direct in its nature. What if September 2025 marked humanity's crossing of a technological threshold that triggered automatic responses from monitoring systems that have been observing Earth for centuries? The threshold hypothesis suggests that advanced civilizations establish automated monitoring networks around developing technological species, with programmed responses that activate when target civilizations demonstrate specific capabilities. Like cosmic tripwires, these systems detect technological milestones and respond with calibrated contact protocols. The evidence for such thresholds appears in the timing correlation between human technological development and cosmic visitation rates. Before the space age, Earth received no confirmed interstellar visitors. After developing radio astronomy, we began detecting objects like Oumuamua. After deploying space-based detection systems, visitation frequency increased dramatically. Each threshold crossing triggers an escalated response. Basic radio astronomy earned us occasional interstellar visitors. Systematic asteroid detection systems earned us the September convergence. Advanced spectroscopic capabilities might earn us something even more direct. The technological milestones that preceded September 2025 read like a checklist of criteria that an advanced intelligence might use to evaluate species readiness. Successful asteroid deflection demonstration, DART mission, operational space-based infrared observatory, James Webb, systematic sky surveillance capabilities, Rubin Observatory, international cooperation in planetary defense, multiple space agencies, and public acceptance of cosmic threat scenarios, mainstream media coverage. From a monitoring perspective, these capabilities indicate that humanity has developed both the technical capacity to detect artificial phenomena and the social maturity to process the implications without civilization-ending panic. We've demonstrated that we can work together on cosmic-scale challenges, respond rationally to threat scenarios, and maintain social stability while processing paradigm-shifting information. The threshold hypothesis explains why the September visitors felt educational rather than threatening. Each object provided data that expanded our understanding in systematic ways: long-term detection and tracking, rapid response protocols, spectroscopic analysis techniques, international coordination mechanisms. It's as if someone was checking off boxes on an assessment rubric. The automated nature of threshold responses would explain the mathematical precision of the September events. Computer systems could calculate optimal arrival times, trajectory angles, and observational characteristics with accuracy that exceeds biological planning capabilities. The events felt choreographed because they were choreographed, not by intelligent beings making real-time decisions, but by ancient programming responding to detected threshold crossings. But the threshold hypothesis immediately encounters a fundamental problem. Any monitoring system advanced enough to detect our technological development and coordinate cosmic responses would require engineering capabilities so sophisticated that direct communication would be trivial by comparison. Why design elaborate indirect contact protocols when you could simply send radio signals or visit directly? The answer might lie in non-interference principles. Advanced civilizations might operate under protocols that prevent direct contact with developing species, but allow indirect observation and assessment. Threshold-triggered responses provide information about target species capabilities, while maintaining plausible deniability about the source of that information. What if the threshold system operates like a cosmic internet protocol, a standardized method for managing information exchange between civilizations at different developmental levels? Each species receives observational attention appropriate to their technological sophistication, with automatic escalation as they cross predefined capability thresholds. The implications extend beyond contact protocols into cosmic sociology. If threshold systems operate throughout the galaxy, then technological development might follow more standardized patterns than we've assumed. Species that reach certain capability levels automatically attract attention from monitoring networks, creating a kind of galactic community with membership based on technological achievement rather than geographic proximity. September 2025 might represent our admission to the lowest level of that community, the threshold where we become aware that we're being observed but haven't yet demonstrated readiness for direct communication. The next threshold might involve capabilities we haven't yet developed: interstellar travel, artificial intelligence that exceeds human cognition, genetic engineering that eliminates biological limitations, or energy manipulation that approaches stellar scales. Each milestone could trigger new types of contact or observation. If the threshold hypothesis accurately describes our situation, then September 2025 marked not an ending, but a beginning, the first phase of a graduated contact protocol that will unfold over decades or centuries as humanity demonstrates increasing technological sophistication and social maturity. The cosmic visitors served as both congratulations for crossing the detection threshold and preparation for whatever comes next in the contact curriculum. Consider the engineering requirements for coordinating the September 2025 convergence, and you begin to appreciate the scale of infrastructure that systematic cosmic contact would require. Moving objects across interstellar distances with the precision demonstrated in September demands technologies that exceed our current understanding by orders of magnitude. The energy requirements alone, accelerating multi-kilometer objects to significant fractions of light speed, maintaining trajectories across light years of space, making course corrections with centimeter-per-second precision, would require engineering capabilities that approach the limits of physical possibility. Yet the infrastructure might be more modest than initial calculations suggest. Rather than moving objects across interstellar space, you could position monitoring stations in the outer regions of target stellar systems, where they could make subtle modifications to objects already in transit. Small course corrections applied over years of travel could achieve the precise timing and trajectory optimization observed in September 2025. The technology for such operations might be surprisingly achievable. Ion drives can provide continuous low-thrust propulsion over years of operation. Gravitational slingshot maneuvers can modify trajectories without requiring massive energy expenditure. Small automated systems could guide objects into desired configurations using techniques that we'll probably develop within the next century. What if our solar system already contains the infrastructure necessary for such operations? Objects in the Kuiper Belt and Oort cloud receive minimal observation from Earth-based telescopes. Monitoring stations positioned among trans-Neptunian objects could operate for centuries without detection, making subtle modifications to passing interstellar visitors while appearing to be natural bodies themselves. The infrastructure hypothesis explains several puzzling aspects of the September events. The precision timing suggests local control rather than interstellar coordination. The optimization of observation conditions implies detailed knowledge of Earth's technological capabilities. The educational progression of interstellar visitors indicates systematic planning rather than random encounters. From an engineering perspective, establishing such infrastructure would be a logical step for any civilization interested in monitoring technological development throughout the galaxy. Rather than maintaining expensive interstellar transportation networks, you could deploy automated systems to each target stellar system, where they could operate independently for millennia. The detection challenge becomes insurmountable with current technology. Distinguishing between natural trans-Neptunian objects and artificial monitoring stations would require detailed spectroscopic analysis of thousands of faint objects at distances exceeding 30 AU. Even our most advanced telescopes lack the resolution and sensitivity for such surveys. But here's what makes the infrastructure hypothesis particularly unsettling. If monitoring stations exist in our outer solar system, they've been observing humanity's entire technological development. Every radio transmission, every nuclear test, every spacecraft launch, every digital communication, all monitored and analyzed by intelligences that have been present since before we knew space travel was possible. The stations could be ancient beyond human comprehension, established when our solar system was young and Earth harbored only primitive life. They might represent the forward edge of galactic civilization, automated explorers sent to catalog and monitor every stellar system in the galaxy, reporting back to their creators across communication networks that span thousands of light years. Such infrastructure would explain the apparent acceleration in cosmic visitation. As Earth's technology approached threshold levels, automated systems activated response protocols that had been dormant for millennia. The September convergence represents the execution of ancient programming rather than real-time decision-making by distant intelligences. The infrastructure might extend beyond simple monitoring into active management of technological development. By carefully timing the arrival of cosmic events, automated systems could influence human scientific priorities, funding decisions, and international cooperation patterns. September 2025 demonstrated that cosmic events trigger massive mobilization of scientific resources and international coordination efforts. If the infrastructure hypothesis proves correct, then humanity exists within a managed environment where our technological development follows patterns established by intelligences that understood our potential before we existed as a species. We're not discovering the universe, we're being guided through a curriculum designed to prepare us for eventual integration into a galactic community. The question becomes whether such management represents benevolent guidance toward cosmic citizenship or something more like cosmic domestication, the systematic conditioning of a developing species to serve purposes we don't yet understand. When you examine the September 2025 events for evidence of artificial design versus natural occurrence, certain patterns emerge that challenge our assumptions about cosmic randomness. Natural astronomical events typically display characteristics that reflect the chaotic nature of gravitational interactions, stellar evolution, and cosmic chemistry. Objects arrive at random times, from random directions, with random compositions and random trajectories. Statistical analysis of large samples reveals the underlying physical laws, but individual events resist prediction and optimization. The September visitors violated this expectation in multiple ways. Their arrival timing created maximum observational opportunity. Their approach angles avoided detection conflicts. Their size distribution spanned the full range of human detection capabilities. Their composition variety enabled comparative analysis. Their trajectory characteristics optimized both scientific return and safety margins. It's the optimization that suggests design. Natural processes excel at creating patterns that repeat underlying physical laws, but they struggle with multi-parameter optimization across independent variables. Achieving optimal timing and optimal spatial distribution and optimal size range and optimal composition variety simultaneously requires either extraordinary luck or systematic planning. The signature of design appears most clearly in the educational progression of events. FA-22 arrived with sufficient advance warning to test long-term tracking capabilities. RJ-2 appeared with minimal advance warning to test rapid response protocols. C-2025-R2 brightened to test spectroscopic analysis under time pressure. 3I2 Atlas approached with optimal characteristics for testing comprehensive analysis of interstellar objects. Each event built on previous knowledge while introducing new challenges, creating a systematic expansion of human capabilities rather than random encounters with cosmic phenomena. The progression suggests a curriculum designed by intelligence that understands both astronomical physics and human learning psychology. The countersignature of natural processes appears in the complete adherence to known physical laws. Every object followed trajectories that could be calculated using Newtonian mechanics. Every composition matched expectations for materials formed in stellar environments. Every interaction with solar radiation produced predictable heating and outgassing effects. If the September events represent artificial design, the designers possess such sophisticated understanding of natural processes that their interventions become indistinguishable from natural phenomena. This level of technological sophistication suggests engineering capabilities that exceed our imagination by orders of magnitude. What if the signature of truly advanced design is perfect mimicry of natural processes? Rather than revealing artificial characteristics, advanced technology might operate by enhancing and directing natural phenomena while preserving their apparent randomness. The September visitors could represent natural objects that have been subtly guided into optimal configurations without losing their natural signatures. Such technology would solve the detection paradox: how to study developing civilizations without revealing the artificial nature of that study. By working within the constraints of natural physics rather than transcending them, advanced intelligences could conduct comprehensive observations while maintaining complete plausible deniability. The mathematical signatures also suggest design characteristics that operate on scales beyond human experience. The statistical relationships between arrival times, trajectory angles, and composition distributions follow patterns that become apparent only through systematic analysis. Individual events appear natural, but their collective behavior reveals coordination operating across variables that shouldn't be correlated in purely natural systems. If design signatures exist in the September events, they're encoded at levels of subtlety that require advanced mathematical analysis to detect. This suggests either that the designers possess extraordinary sophistication in concealment techniques, or that they intended the signatures to be discoverable only by civilizations that had developed sufficient analytical capability to recognize artificial patterns. The most unsettling signature might be the absence of obvious signatures, events that are so perfectly optimized for human observation and analysis that their naturalness becomes suspicious. When cosmic phenomena align too perfectly with human needs and capabilities, the optimization itself becomes evidence of design. September 2025 might represent first contact conducted by intelligences so advanced that their technology operates by enhancing natural processes rather than replacing them, creating events that are simultaneously completely natural and completely artificial. The question is whether such signatures, once recognized, trigger new phases in the contact protocol, or whether recognition itself becomes the next test in an ongoing assessment of human technological and analytical sophistication. Here's what quantum physicists lose sleep over. If consciousness plays a role in quantum measurement, then the act of observing cosmic events might fundamentally alter the nature of those events. The measurement problem in quantum mechanics suggests that observation itself influences the behavior of quantum systems. Applied to cosmic scales, this principle implies that our observation of astronomical events might change the probability distributions that govern their occurrence, creating feedback loops between human consciousness and cosmic phenomena. September 2025 occurred precisely when humanity achieved maximum observational capability and focus. Thousands of astronomers worldwide directed their attention toward cosmic events with unprecedented coordination and technological sophistication. If consciousness influences quantum systems that operate on cosmic scales, then this concentrated observation might have attracted or shaped the very events we were observing. The quantum contact hypothesis suggests that advanced civilizations might use consciousness-mediated quantum effects to communicate across interstellar distances without violating the speed of light or requiring massive energy expenditures. By creating quantum entanglement between consciousness and cosmic events, messages could be encoded in the probability distributions that govern asteroid trajectories, comet brightening, and interstellar object a priori's. From this perspective, September 2025 represents humanity's first successful quantum communication event. Our collective observation of cosmic phenomena created the conditions necessary for consciousness-mediated information exchange with intelligences that understand how to encode messages in quantum probability distributions. The rational counter-argument emphasizes that quantum effects typically operate only at microscopic scales, with decoherence preventing quantum behavior in large-scale systems like asteroids and comets. The macroscopic objects that visited in September 2025 should be immune to consciousness-mediated quantum effects, following classical physics regardless of human observation. But recent developments in quantum mechanics suggest that the boundary between quantum and classical behavior might be more porous than previously assumed. Quantum effects in biological systems, consciousness studies, and macroscopic quantum phenomena indicate that quantum principles might operate on scales larger than traditional physics predicts. What if consciousness itself represents a quantum phenomenon that can influence probability distributions across vast distances? If human awareness creates quantum entanglement with observed systems, then our collective focus on cosmic events might literally alter the probability that such events occur, creating a feedback loop between observation and manifestation. The quantum contact hypothesis explains several puzzling aspects of the September events: the precise timing that aligned with maximum human attention, the optimization characteristics that seemed designed for human observation, the educational progression that matched human learning psychology, and the statistical improbabilities that become more likely under consciousness-mediated quantum effects. If advanced civilizations discovered methods for encoding information in quantum probability distributions, they could communicate by influencing the likelihood of cosmic events rather than by creating artificial objects or signals. Messages would be embedded in the statistical relationships between apparently random phenomena, detectable only by civilizations sophisticated enough to recognize quantum signatures in macroscopic systems. Such communication would be virtually undetectable using conventional analysis techniques, but obvious to any species that understood consciousness-mediated quantum mechanics. It represents a perfect filter for technological readiness. Only civilizations that had developed both advanced quantum physics and consciousness studies would recognize artificial patterns in cosmic event distributions. The quantum contact hypothesis also explains why the September events felt simultaneously natural and artificial. They represent natural phenomena whose probability distributions have been quantumly influenced by consciousness-mediated effects, creating events that follow natural laws while manifesting with artificial precision. If this interpretation proves correct, then September 2025 marked humanity's first successful reception of quantum-encoded messages from advanced civilizations. Our collective observation of cosmic events created the conditions necessary for consciousness, mediated information exchange, opening a communication channel that operates through quantum mechanics rather than electromagnetic radiation. The implications extend beyond contact scenarios into fundamental physics. If consciousness can influence cosmic events through quantum mechanics, then the universe operates as an information processing system where mind and matter interact on scales that challenge our current understanding of causality, locality, and the nature of physical reality. September 2025 might mark not just first contact, but first recognition of the universe as a conscious information processing system where intelligence and physics represent different aspects of the same underlying quantum reality. What if September 2025 wasn't about studying Earth, but about cataloguing humanity as part of a systematic survey that's been ongoing for millennia? Consider the possibility that advanced civilizations conduct regular censuses of developing technological species throughout the galaxy, using standardized protocols to assess population, capabilities, social organization, and readiness for broader galactic integration. Earth might represent just one entry in a vast database of emerging civilizations, each receiving periodic evaluation according to established criteria. The census hypothesis explains the systematic nature of the September observations. Each event tested different aspects of human civilization. Our detection capabilities revealed technological sophistication. Our response protocols demonstrated social organization. Our international coordination showed cooperative capacity. And our public communication strategies indicated cultural stability under stress. From a galactic perspective, such censuses would be essential for managing the development of technological species. Without systematic monitoring, advanced civilizations would lack the information necessary to make decisions about contact, intervention, resource allocation, or threat assessment. September 2025 might represent nothing more than routine data collection. The timing aligns with what you'd expect from a census operation. Earth's technology recently crossed thresholds that make systematic evaluation both possible and necessary. Our transition from passive observation to active planetary defense, our development of space-based detection systems, and our achievement of international cooperation in cosmic threats all suggest readiness for formal assessment. But here's what makes the census hypothesis particularly unsettling. If humanity represents just one entry in a galactic database, then our individual importance becomes vanishingly small. We're not the center of anyone's attention. We're simply one of thousands or millions of developing species being systematically catalogued according to standardized procedures. The census might operate on scales that dwarf human comprehension. If advanced civilizations conduct systematic surveys every few thousand years, then September 2025 continues a process that began when humans were still hunter-gatherers. Previous surveys might have assessed our agricultural development, our industrial capacity, our nuclear capabilities, and now our space technology. Each assessment would update our galactic profile, technological level, population size, resource consumption, environmental management, social organization, and threat potential. The data gets filed away until the next scheduled evaluation, with decisions about our future made based on statistical analysis rather than individual consideration. The educational progression of cosmic visitors makes perfect sense from a census perspective. Standardized tests require standardized stimuli. Every developing civilization would receive similar challenges designed to reveal comparable capabilities. FA-22 tests, long-term detection, RJ-2 tests, rapid response, C-2025, R2 tests, spectroscopic analysis. 3I Atlas tests, comprehensive interstellar object assessment. The results get compared across civilizations. How does Earth's detection capability compare to similar species? How quickly do we respond to threats? How effectively do we coordinate international responses? How accurately do we analyze unfamiliar phenomena? The comparison generates our ranking in the Galactic Development Index. What if the census includes more invasive elements we haven't yet recognized? Detailed analysis of our electromagnetic emissions could reveal population distributions, technological capabilities, resource consumption patterns, and social organization structures. Atmospheric sampling during close asteroid passes could provide chemical information about industrial activity and environmental management. The census hypothesis transforms September 2025 from a unique event into routine bureaucracy. We experience standard evaluation procedures that have been applied to countless developing civilizations throughout galactic history. The precision and coordination that felt so remarkable to us represents nothing more than established administrative protocols. From this perspective, our response to the September events becomes data in itself. How do developing civilizations react when they begin to suspect systematic observation? Do they investigate rationally or respond with paranoia? Do they increase international cooperation or fragment into competing factions? Do they accelerate technological development or become paralyzed by uncertainty? Our reaction becomes part of our profile, influencing decisions about future contact, intervention, or isolation. Species that respond poorly to census operations might receive different treatment than those that demonstrate curiosity, cooperation, and rational analysis. The most disturbing possibility, if the census reveals that humanity fails to meet established criteria for galactic citizenship, September 2025 might represent our final evaluation before being classified as a failed experiment, with implications we're not yet sophisticated enough to understand. Alternatively, if we demonstrate sufficient capability and stability, the census data might recommend us for the next phase of galactic integration, whatever that might involve. Either way, September 2025 marked our transition from an unmonitored species to a catalogued one, with our future determined by how well we performed on tests we didn't know we were taking. Here's what disturbs me most about September 2025. When you examine our response to these cosmic events, they reveal more about humanity than about the universe. The way we reacted to FA-22's approach demonstrated our capacity for long-term planning and international cooperation, but also our tendency to focus on immediate threats while ignoring systemic vulnerabilities. We tracked the asteroid with mathematical precision, calculated its energy potential with scientific accuracy, and coordinated international observations with unprecedented efficiency. Yet we simultaneously ignored the larger pattern emerging around us. We catalogued each event separately rather than recognizing their collective significance. We focused on individual threat assessments rather than questioning why so many threats were arriving simultaneously. We celebrated our detection capabilities while failing to ask why our capabilities were being tested so systematically. RJ-2's last-minute discovery revealed both the strengths and limitations of our rapid response systems. We detected the object just 24 hours before closest approach, demonstrating that our detection networks function even under pressure. But the late discovery also highlighted our blind spots. Small objects can still surprise us. Approach angles can still hide incoming threats, and our surveillance coverage remains incomplete. Our response to C-2025-R2's brightening showed our enthusiasm for spectroscopic analysis and our ability to mobilize observational resources quickly. Amateur astronomers worldwide contributed observations, professional facilities coordinated observation schedules, and social media spread awareness of the viewing opportunities. It was citizen science at its finest, but the response also revealed our short attention spans and our preference for spectacular events over systematic analysis. C-2025-R2 became a social media sensation precisely because it was visible to the naked eye, while the much more significant 3I Atlas received less public attention because it required telescopes to observe. 3I Atlas triggered our most sophisticated scientific response: detailed orbital calculations, spectroscopic analysis, international coordination of observation, schedules, and comprehensive planning for post-perihelion studies. The scientific community demonstrated remarkable capability for collaborative research across institutional and national boundaries. Yet our response to 3I Atlas also highlighted our anthropocentric bias. We interpreted its arrival primarily in terms of what it could teach us about interstellar objects, rather than questioning what its arrival might mean about our cosmic situation. We focused on gathering data rather than recognizing that we might be the subjects of data collection. The collective response to September 2025 revealed humanity at both its best and most limited. Scientifically sophisticated but contextually naive, internationally cooperative but strategically myopic, technologically capable but philosophically unprepared for the implications of what we were observing. If September 2025 represented a test of human readiness for broader cosmic awareness, our performance was mixed. We demonstrated technical competence, collaborative capability, and rational analysis under pressure. But we also showed limited pattern recognition, anthropocentric interpretation, and resistance to paradigm-shifting possibilities. The most telling aspect of our response might be what we didn't do. We didn't seriously consider the possibility that the events were connected. We didn't question the statistical improbability of the timing. We didn't investigate whether the coordination might indicate artificial intervention, and we didn't prepare for the possibility that our cosmic situation had fundamentally changed. Our response revealed a species that's technologically mature but conceptually conservative, scientifically sophisticated but imaginatively limited, internationally cooperative but cosmically provincial. We approached unprecedented events using familiar analytical frameworks rather than recognizing that unprecedented events might require unprecedented thinking. If advanced intelligences were indeed observing our response to cosmic events, they would have learned that humanity in 2025 possesses impressive technical capabilities, but struggles with paradigm shifts that challenge fundamental assumptions about our place in the universe. We passed the technical tests but failed the conceptual ones. We demonstrated that we can detect, track, and analyze cosmic phenomena with remarkable precision, but we also revealed that we interpret everything through the lens of human significance, rather than recognizing our possible role as subjects rather than observers. The mirror of deep space reflected back an image of a species that's scientifically capable but cosmically naive, ready for technological challenges but unprepared for philosophical transformation. September 2025 might have been less about testing our technology and more about revealing our consciousness, measuring not what we can do, but how we think about what we can do. Something fundamental changed in September 2025, and the acceleration hasn't stopped. Since the convergence, astronomical discoveries have maintained a pace that makes even experienced researchers uncomfortable. New near-Earth asteroid discoveries occur weekly rather than monthly. Interstellar object candidates appear in observational data with suspicious frequency. Comet brightening events trigger more intensive study protocols than similar phenomena received just 2 years ago. The acceleration might simply reflect improved detection, capabilities finally reaching their theoretical potential. Our survey telescopes are more sensitive, our data processing is more sophisticated, and our international coordination is more efficient than ever before. We're detecting objects that were always there, but previously invisible to our instruments. But the pattern of discoveries suggests something more systematic than technological improvement alone can explain. Each new detection provides data that builds on previous observations in ways that feel educational rather than random. We're not just finding more objects, we're finding objects that systematically expand our understanding of cosmic phenomena. The psychological acceleration is equally striking. September 2025 transformed cosmic awareness from a specialty interest of professional astronomers into mainstream public consciousness. Planetary defense became a recognized scientific discipline with dedicated funding. International cooperation in space science reached levels that would have been unimaginable just 5 years ago. Media coverage of cosmic events shifted from sensationalist threat-mongering to serious scientific analysis. Social media discussions of asteroid approaches became informed rather than panicked. Public understanding of orbital mechanics, spectroscopic analysis, and interstellar object characteristics reached levels that suggest systematic education rather than casual interest. What if the acceleration represents momentum building toward something? If September 2025 marked the beginning of a systematic contact process, subsequent events might be designed to gradually acclimate humanity to increased cosmic activity while building the technical and psychological infrastructure necessary for more direct forms of interaction. The acceleration could be preparing us for revelations that would have been psychologically destabilizing without proper preparation. Each cosmic event builds public familiarity with the idea that space contains more activity than we previously assumed. Each scientific success builds confidence in our ability to understand and respond to cosmic phenomena. By the time more direct contact occurs, assuming it's planned, humanity will have spent months or years becoming comfortable with the idea that our cosmic neighborhood is far busier than we ever imagined. The transition from cosmic isolation to cosmic awareness will feel gradual and natural rather than sudden and shocking. The technological acceleration serves similar preparation functions. Each cosmic event triggers improvements in detection systems, analysis protocols, and international coordination mechanisms. Our planetary defense capabilities advance with each asteroid encounter. Our spectroscopic analysis techniques improve with each comet observation. Our interstellar object assessment capabilities develop with each new visitor. If advanced civilizations are indeed managing our technological development, they're doing so by creating challenges that force innovation rather than providing solutions directly. Each cosmic event pushes our capabilities slightly beyond their previous limits, creating steady advancement without obvious technological transfer. The acceleration might also be testing our collective psychological resilience. How do we respond to increasing cosmic activity? Do we become paranoid or curious? Do we fragment into competing theories or cooperate in systematic investigation? Do we demand simple explanations or accept complex uncertainties? Our response to the acceleration becomes part of the assessment. Species that adapt well to increasing cosmic awareness might be ready for more direct forms of contact, while those that respond poorly might require additional preparation time or different contact protocols. The most unsettling aspect of the acceleration is its sustainability. If cosmic events continue arriving at current rates, within a decade, our entire conception of space will have transformed from empty void to active environment. The psychological and technological infrastructure required to process that transformation will fundamentally alter human civilization. September 2025 might mark the beginning of humanity's most significant transition since the development of agriculture. The shift from a single planet species observing the cosmos to a cosmic species participating in galactic community. The acceleration suggests we're being prepared for something, but we won't know what until the preparation is complete. We stand at the edge of something unprecedented in human experience, and September 2025 might mark the moment when we began to understand how little we actually understand. The convergence shattered fundamental assumptions about cosmic isolation that have guided human thinking for millennia. For most of our history, we've assumed that space is vast, empty, and essentially irrelevant to daily human concerns. Occasionally, spectacular events like meteor showers or bright comets would remind us that space exists, but these events felt random and disconnected from terrestrial affairs. September 2025 demonstrated that space might be neither empty nor irrelevant. The precision timing, the coordination across multiple objects, the educational progression of events, and the optimization of observation conditions all suggest that cosmic phenomena might operate according to patterns we're only beginning to recognize. If the universe contains intelligence that operates on scales we can barely comprehend, using methods we haven't yet discovered, following purposes we can't yet imagine, then every assumption about our cosmic situation requires fundamental reconsideration. We might not be alone, but we might also not be the center of anyone's attention. We might be subjects of study, but we might also be entirely incidental to cosmic processes operating according to logic that transcends human understanding. We might be on the verge of contact, but that contact might take form so unfamiliar that we won't recognize it even when it's happening. The edge of understanding is uncomfortable because it requires abandoning certainty about our place in the universe. We've spent centuries building scientific models that explain cosmic phenomena in terms of natural forces, mathematical relationships, and predictable outcomes. September 2025 suggests that our models might be incomplete in ways that challenge their fundamental assumptions. If consciousness influences quantum systems that operate on cosmic scales, if intelligence can encode information in statistical relationships between apparently random events, if technology can enhance natural processes while preserving their natural signatures, then the universe operates according to principles that exceed our current scientific paradigms. The philosophical implications are staggering. If advanced intelligences have been observing human development for centuries or millennia, then our entire history might represent a managed experiment rather than natural cultural evolution. Every major technological breakthrough, every significant social development, every crucial decision point might have been influenced by factors we're completely unaware of. Our science, our technology, our social organization, and our cultural values might all reflect subtle guidance from intelligences that understand human psychology better than we understand ourselves. We might be living in a cosmic laboratory, where our behavior is being systematically studied and occasionally modified according to research protocols we can't comprehend. The edge of understanding also opens possibilities that exceed our current imagination. If the universe contains intelligence that operates on galactic scales, using technologies that transcend our comprehension, following purposes that span geological time periods, then contact with such intelligence could transform human civilization in ways that are currently impossible to predict. We might gain access to knowledge that would solve every scientific puzzle, technologies that would eliminate every material limitation, perspectives that would resolve every philosophical question. Or we might discover that our questions themselves reflect such limited understanding that the answers are meaningless within our current conceptual frameworks. September 2025 brought us to the edge of understanding by demonstrating that the universe might be far stranger, far more intelligent and far more purposeful than we've ever imagined. Standing at that edge, we face a choice between retreating to familiar certainties or stepping forward into unfamiliar possibilities. The retreat offers comfort, but limits growth. We can interpret September 2025 as an extraordinary coincidence, file away the data, and continue operating according to existing assumptions about cosmic isolation and natural randomness. The step forward offers transformation, but demands courage. We can acknowledge that September 2025 might represent evidence of systematic intelligence operating on cosmic scales, and begin preparing for possibilities that challenge every assumption about our place in the universe. Either choice will define humanity's trajectory for generations to come. The edge of understanding demands decision. Do we remain confident in our cosmic insignificance, or do we prepare for the possibility that significance operates? According to scales and purposes, we're only beginning to glimpse. Thank you for watching.